everyone, good evening to all. Welcome to Civilianz. Am I audible? Okay. So we are introducing a new revision series section for SSC JE aspirants, especially for civil engineering students. So today we are discussing environmental engineering subject. So basically I have divided the all subject into three parts. Everyone know that. First one raw water engineering, second one wastewater engineering, and last part include municipal solid waste and air pollution, etc. So today I pick some question from raw water engineering. So shall we start our class? Okay, so please put your answer in our chat box. Okay, let's start our question number 1. Which of the following is not a method for forecasting population used for estimating water requirement of a town? So 4 options are given here: zoning method or master plan method, and arithmetical increase method, geometrical increase method, and Prismol method. This master plan, okay? And put your answer in our chat box. So option A or option B, option C, option D. Okay, so in this question, mainly in question already mentioned, the following is not a method for forecasting population. So everyone know that there's too much, so many population forecasting method occur. So first option, zoning method. Zoning method is a part of measuring, find out the population of population. So first question, which of the following is not a method for forecasting population used for estimating the water requirement of a town? 4 options are given. First one, zoning method, arithmetic increase method, geometrical increase method, Prismodal method. Put your answers in our chat box. Okay. So in this question, they already mentioned not a method for forecasting population. Not a method. Okay. So should focus on this point. Not a method. Okay. Everyone know all 6 methods are occur for forecasting population. So first method, zoning methods. Obviously, it's a type of the forecasting population method, and second one B and C. Old town, already developed town. Okay, and second geometrical increase method, the newly developed town. This method is used for calculating the population, calculating newly or developing town. So these 3 methods are used for forecasting population. So last one, what is Prismodal method? So Prismodal method, so this method is used to calculating volume of earthwork. So this method we usually see in surveying. Okay. So Prismodal method, it's not a method for population forecasting. Okay. So we can select option D. Okay, option D. I saw some answers option D. So option D, Prismodal method is not a method for population forecasting. Okay, it's clear? So next question. Next question. It's a simple question. The population forecasting method, the best suited when the growth rate is having decreased trend and the city heading towards a saturation. Saturation. Option A, arithmetic. Option B, geometric. Option C, graphical. Option D, decrease the rate of growth. In this question, clearly mentioned the city decreasing trend, having the growth rate having decreasing trend, and city is heading towards saturation. Towards saturation. Saturation means the rate of growth almost approximately end. Okay. Which one? Please put your answer in our chat box. Just comment options A, B, C or D. Okay. So arithmetic increase method obviously is old, we use it to for old city already discussed in previous question. And geometric increase method, the increasing rate is not used in saturation point. Okay. Graphical also it's used in growth rate calculation in say not for the saturation. But decreasing rate of growth, that is this option is mainly used to calculate growth rate in saturation. Saturation means there is no the almost all developments, all growth rates is reach the peak. Okay, reach the peak. There is no other rate happen. So saturation is happen. So option D is the answer, decrease the rate of growth. Okay, actually it's a simple question. Can go to the next question. This is also very simple question. A town water supply scheme is commonly designed for population. Option A at present year, option B after 1 decade, option C after 2 decades, option D after 3 decades. Clearly read our question. Water supply scheme is commonly designed for population. Designed. Okay. Please comment your answers. Option A, option B, option C, option D. Actually, simple question. In this question, already they mentioned design for a population. First of all, we can eliminate one option from these options. Which one? The question already mentioned design. In every cases for a design of anything, we can use the future value, okay, future population value. So in this option A is indicate at present year, at the present year. So we can directly eliminate option A. Option A is not for this answer because we didn't consider the present population for the design of a water scheme or water supply scheme. So B, C or D, which one? And also B, C, D options are mentioned in decades. Okay, decades. What is decades? What do you mean by decades? One decades equal to how many years? Please answer. 10 year. So you have to study the design period of water supply scheme. We already studied the design period of pipe, design period of distribution system, design period of water supply schemes. Usually we consider 30 years. Okay. Usually we consider 30 years. 30 years means how many decades? 30 years. 30 years equal to 3 decades. So after 3 decades, this is the answer. Option D. Option D. Okay, option D. Option D is the answer. Okay, so next question. The daily per capita consumption of a water apparently increases higher standard of living of people, availability of sewage in city, metered water supply, or some and potable quality of water. Choose the correct answer below. Okay. Option A, B and D. Option B, C and D. Option C, A, C and D. Option D, A, B and C. Actually, they are giving some condition for consumption of water. Okay, some living conditions. You should choose correct condition for the daily per capita consumption of water. So how to depends this condition with consumption of a water. First you should have to think how to depend this consumption and these conditions. Okay. Comment your answer. Option A, B, C or D? Okay, A. Okay. 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 So, first condition we can take first condition. In option A, higher standard of living of people. Higher standard of life. So, we can living in higher standard. We can, we didn't think about the rate of water consumption. So, that condition, in that case, the high standard of living is directly proportion to the consumption. Okay, so this is directly proportion to the consumption. So we can take this one, option A. And second one, availability of sewer in a city. So obviously the availability of sewer in cities increases, obviously consumption also increases. Okay, the rate of consumption also increases. So we can take this also. And next, metered water supply. What is metered water supply? So in this metered water supply, we have to pay the water for wastewater and normal water. So in this condition, the consumption rate decreases. Okay, so the rate and we use it to a measure or device for the metering the water. So in this condition, it's inversely proportional to the consumption. So we cannot consider this option. Okay, so next option D, the wholesome and potable quality of water. In every cases the quality is directly proportional to the consumption of water. So the quality of water increases, consumption also. In every area the quality of water increases, obviously the consumption also increases. So these are also directly proportional. So option A, option B, option D, these are directly proportional to the consumption. So in our case, the daily capita consumption of water apparently increases. So increases with the higher standard of living and availability of sewer in city and potable quality of water. So we can select A, B, D. So option A. Okay. Okay. So, you can go to the next question. Next question. Actually, very simple question. For a public water supply, the threshold number for taste and odor should not be more than option A 1, option B 2, option C 3, option D 4. So, from this area, we have to study lot of limits value in this chapter. That's chemical, physical characteristics, biological character of water. So I think these values are from physical characteristics of water. So we know that we have two limits value, acceptable limit and maximum permissible limit. Okay. So in this case, they are asking the should not be more than, should not be. So the order values, threshold order value, taste and order should not be more than. In this option, they are already given the both acceptable limit and maximum permissible limit value. So the way confusion in the options, option A, option C. These are the values of threshold order number, but they are asking should not be more than, should not be more than. That means maximum permissible limit. Okay, maximum permissible limit of the threshold order number. Which one? Which one? 1 or 3? 1 or 3? Please comment your answers in that box. 1, option A or option C? Option C, that is threshold order number 3. 3 is used, should not, this is the maximum permissible value. Okay, that should not be more than 3, should not be more than 3. So it's very important. This is acceptable limit value. This also, what the range is 1, 2. This is acceptable limit, maximum permissible limit. Please note the values. Okay. So not confused with the options. Okay. Can you go to the next question? If the expected turbidity of the water is more than 500 ppm, the turbidity meter used for the analysis. Jackson turbidity meter, Helios turbidity meter, Bayes turbidity meter, any one of them. So, should focus in a range. Okay. They are already mentioned a range 500 ppm, and in option here 3 types of turbidity meter. Please answer option A, option B, or option C. Actually, in Jackson turbidity meter, usually we use in case of high turbidity. That means the turbidity is greater than 25 ppm. Okay. So, in this case, the turbidity of the water is more than 500. That is including this case Jackson turbidity meter. So, Jackson turbidity meter usually we used in high turbidity. Okay, high turbidity range. So, 500 ppm is high. Is it high turbidity? Is it high turbidity? Yes. Is it high turbidity? So, Jackson turbidity meter is used. Just write this point. Jackson turbidity meter used in high turbid water, and also Bayes turbidity meter. This is used in low turbidity water. Actually, 1 to 2 ppm turbid water we can use Bayes turbidity meter. Okay, these 2 points are it's the major points in turbidity meter area. Okay. So, Jackson turbidity meter, use Jackson, Michael Jackson. So, it's a high level, this very non people. So, Jackson, high turbidity meter. Bayes turbidity meter is used in low turbidity meter. Okay. So, the option A is the answer. Option A is the answer. Okay, note. Please note the answer. And next question. The finely divided dispersion of solid particles which are not visible to a naked eye and can be removed by ordinary filter and known as suspended impurities, dissolved impurities, colloidal impurities, and none of this. Actually, it's very simple question. You can answer very easily. Okay. Which one? A, B, C, or D? B, D, yeah. Yeah. So you have to consider the 1 beaker of water, anything. Okay, 1 beaker of water. So we added water. So we added a finely divided solid particle in this water. So in first case, some amount of particle fully dissolved in this water, fully dissolved, and some amount of particle suspended in this, the bottom part. Okay, that is suspended particle, and other amount of particle is dissolved or colloid in this water. Colloidal in this water. The colloidal impurities we cannot see with our naked eye. That is, for example, milk, okay, rice water. This water is including very finely divided solid particle. That is the colloidal impurities. So, the finely divided dispersion of solid particle which are not visible to the naked eye, that is which one? Colloid particle. So, dissolved impurities and suspended impurities we can see in our eye. Suspended impurities are present in this side, bottom side. Suspended particles are present in one end. And the fully dissolved in water we cannot see. And colloidal impurities, so the colloidal impurities, so I am already given that 2 examples. So, the colloidal particles we cannot see with our naked eye. Okay, so option C, this is a previous year question, okay, not the previous year question. So next question, it's a problem. So first you should write the question carefully and draw this figure, this chart. For a sample of water with a ionic composition shown in the figure below, the carbonate and non-carbonate hardness concentration in milligram per liter as CaCO3 respectively are, I'm giving a chart, Ca2 plus Mg2 plus Na2 plus, they are already given milliequivalent per liter 0.457 and 3.5. Okay, is it visible? Visible? Okay. So option A 175 and 75, option B 250 and 200, option C 200 and 50, option D 50 and 200. Okay, we have to find out carbonate and non-carbonate hardness. Carbonate and non-carbonate hardness. What is hardness? What is hardness? The hardness is caused by multivalent cation. Multivalent cation. So they are given one figure here. So which one? Ca2 plus and Mg2 plus Na plus. These HCO3, SO4. These the cation and anions given in figure. So hardness means it's caused by multivalent cation. So which are the multivalent cation in this figure? Which are? Ca2 plus and Mg2 plus, multivalent cation. So Ca2 plus and Mg2 plus causes hardness in this water. So these are the two particle the causes hardness. So we can write that we have to find out carbonate hardness and non-carbonate hardness. So first how can find out carbonate hardness and non-carbonate hardness? Carbonate hardness is the minimum of total hardness and total alkalinity. So first of all, we have to find out total hardness and total alkalinity. Then after that, we have to we can find out the minimum of these values, and we can select the total hardness or total alkalinity. Which one is minimum? That is the carbonate hardness. Okay. So first, what is how to calculate total hardness? Total hardness equal to the concentration of Ca2 plus divided by equivalent weight of Ca2 plus into equivalent weight of CaCO3. Okay, plus concentration of Mg2 plus divided by equivalent weight of Mg2 plus into equivalent weight of CaCO3. Okay, and already in this figure given the Mg2 plus value, but you have to clearly due to just consider the values of Ca2 plus. What is Ca2 plus? Ca2 plus equal to 4 and Mg2 plus equal to 0 to 4 Ca2 plus and 0 to 5 equal to Ca2 plus Mg2 plus. So Mg2 plus equal to 5 minus 4. So what the value of Mg2 plus? 1 milliequivalent per liter and Ca2 plus equal to 4 milliequivalent per liter. Just milliequivalent per liter. What is milliequivalent per liter? Milliequivalent per liter, that is Ca2 plus milliequivalent per liter, Ca concentration of Ca2 plus divided by equivalent weight of Ca2 plus. That's molarity. So normality. Sorry, normality value. So that is equal to 4. That is 4 into equivalent weight of CO3 50 plus what is equivalent to Mg2 plus value? Mg2 plus value equal to in figure 1 milliequivalent per liter. That is the concentration of Me2 plus divided by equivalent weight of Me2 plus equal to in what is 1. 1 into 50. Okay, the milli equivalent, it is equal to milli equivalent per liter. Okay, it is equal to milli equivalent per liter. That in already given in our question 4 and 1. Okay, so 4 into 5 plus 1 into 50. So 5 into 50, 250 equal to total hardness. Okay, so next we have to find out total alkalinity. Total alkalinity also find this same method. The concentration of H, what is the cause of the so total alkalinity equal to the total alkalinity causes by HCO3. The concentration of HCO. How to calculate this? The concentration of HCO3 divided by equivalent weight of HCO3 into equivalent weight of CaCO3. Okay. Then what is the value of HCO3? 0 to 3.5. That's 3.5 milli equivalent per liter. So milli equivalent per liter equal to this value. So 3.5 into 50, that is equal to 175. So what is carbonate hardness? Is the minimum of total hardness or total alkalinity. What is the minimum value? 175. 175. So directly we can select the option A, 175, the carbonate hardness. So we have to find out carbonate hardness and non-carbonate hardness. What is non-carbonate hardness? Non-carbonate hardness equal to total hardness minus total, so carbonate hardness. Total hardness, how much total hardness? 250. 250 minus 175 equal to 75, the answer. So carbonate hardness equal to 175 and non-carbonate hardness equal to 75. So we can select option A. Okay. Option A. Very simple question. In this question, you should focus on only this unit, milli equivalent per liter. Okay, milli equivalent per liter. Okay, and also you should just consider the value 0 to 4 Ca2 plus, 0 to 5 Ca2 plus plus Mg2 plus. Should not consider the Mg2 plus value is 5. Is not correct. The Mg2 plus value is 5 minus 4 equal to 1. Okay. So, next question. Next question, it's a problem. Two samples of water A and B have pH value of 4.4 and 6.4 respectively. Then how many times the sample A is more acidic than sample B? Okay, actually it's a previous year question. It's a GATE previous year question. One more question. So you can select the answer directly from this option. Option A 0, option B 100, option C 50, option D 200. So in this question, what is pH? pH value? What do you mean by pH? pH equal to minus log concentration of H plus. That means log 1 by H plus. That's why it's writing P. Okay. So log minus log H plus. So in this question already mentioned the sample A and sample B. Two samples are given. The pH value of sample A 4.4 pH value and pH value of B 6.4. So pH value 4.4. Put here. So H plus value, the concentration of H plus, directly we can write 10 raised to minus 4.4. Okay. So we can put the value in pH. Then we can directly write here the concentration of H plus equal to, consider the log and 10 raised to minus 4.4. Obviously, in sample B, H plus ion concentration equal to 10 raised to minus 6.4. What's our question? How many times sample A is more acidic than the sample B? How many times? So we have to find out the times value. How many times value? So the ratio, we have to find out the ratio of the sample A and sample B. So sample A ratio divided by sample B H plus ratio. That means 10 raised to minus 4.4 divided by 10 raised to minus 6.4. So calculation 10 raised to minus 4.4 plus 6.4. Okay, directly we can write 10 square, that is 100. So option B is the answer. Very simple question. Very, very simple question. Okay, option B is the answer. Okay. Option B. Okay, okay. Option B is the answer. So next question. The cord screens are normally kept in inclined at about 45 degrees 45 to 60 in horizontal. So as to A, option A. Then the question is the cord screens are normally kept in inclined at about 45 degree to 60 degree to horizontal. So as to the decrease the opening area to reduce the flow velocity. Option B, decrease the opening area to increase the flow velocity. Increase the opening area to reduce the flow velocity. And increase the opening area to increase the flow velocity. So which one is correct? Comment. Please comment. Option A. So in every cases, in screening process, always the screen kept in inclined to horizontal. Kept inclined to horizontal. We make a angle 40 or 30 degree to 60 degree. 40 degree to 60 degree. Why? Why? So why we always kept the inclined position, or obviously we kept an angle 40 degree to 60 degree. Why? Which option is correct? So decreasing opening area reduce. Which one? The inclined position means increase or decreasing area. Which? Increasing surface area. Okay, that means increasing open area to reduce flow velocity. That will be increase the efficiency of screening. Okay, the more particle we can remove from this screen. Okay, that is the principle behind this inclined position. Okay, so what is the principle behind? That is the always we kept the incline about 45 degree to 60 degree. That means increase the opening area or surface area and reduce the flow velocity. Flow velocity reduce means the effect of the screening is increase. Effect of the screening is increase. So efficiency also increase. Okay, so option C is the correct answer. Okay, so fine. So obviously always we kept the screen in inclined position. Why? Why increase the opening area or surface area? That reduce the flow velocity. So in that case we can remove the more particle. So the efficiency also increase in that area. Okay, very simple question. Next question. Okay, it's very, very simple. In a specific gravity of a suspended particle is increased from 2 to 3. 2 to 3. Sorry. 2 to 3. The settling velocity will not change, get doubled, get increases by 1.5 times, get increases by 2.25 times. Actually, it's very simple question. Everyone know one equation, settling velocity equation. You can directly substitute this value into the equation. You will get the answer. Okay. So we have two values in suspended particle values 2 and 3. First, you should write that equation, settling velocity equation in your notebook and just substitute these values in that suspended particle. Okay. What is our equation? What's our equation? Settling velocity equation. Vs is equal to g into d square g minus 1 into 80 into mu. Very simple equation. Okay. So, in specific gravity of suspended particle is increases from 2 to 3. So, we have two values of specific gravity 2 and 3. Okay. You have to substitute this value in G. What is specific gravity in this? G. So, you have to substitute this value in G position and we will get answer. Okay, in first case, G value, what is G value? 2. So, first case G value is 2. So, Vs equal to G into D square in G. G equal to, what is G? 2 minus 1 divided by 80 mu. That is equal to G D square divided by 82 minus 1, 1. So, 80 mu in first case. In second case, G value equal to 3. Okay, G value equal to 3. So, Vs equal to G into D square. What is G value? 3 minus 1 divided by 80 into mu. Okay, so in this case we can write 2gd square divided by 8. So what's the difference? What is the difference? In this case, gd square divided by 80 mu. In this case, 2gd square divided by 80 mu. So the value doubled. The value get doubled. Okay. Then option number, option B. It's a correct answer. Okay. 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 So option B, then 2 to 3, the settle velocity will get doubled. Okay. So can you go next question? Sorry. Okay. Question. So what's the problem? So 24 lakh liter of water pass through a sedimentation tank which has rate of flow 300 cubic meter per day. The detention time for a tank is option A 1.2 hours, option B 8 days, option C 3 hours, option D 0.875 hours. It's a very simple problem. We can write the answer from units also. Okay. Actually, we have only two values here, one volume and discharge values. So one equation is there, one basic equation is there. Anyone tell the equation? Do you know that equation? Volume, time, discharge relation equation. It's very basic equation. Q equal to V divided by time, volume divided by time. Discharge is equal to volume divided by time. That is meter cube per day. Okay. So, in our question, They already given the volume, the liter of water, that is meter, the liter, we can convert into meter cube. So V equal to 24 lakhs. Okay. So that is liter, we can convert into meter cube. So meter cube divided by, or into 10 raised to minus 2 divided by 1000, we can write the 2400 meter cube. Okay. And Q value, discharge, the sedimentation, the pass the rate of flow 300 meter cube per day. So Q equal to rate of flow 300 meter cube per day. Okay, so we can write T equal to, we have to find out what is, we have to find a detention time for the tank, detention time. So we have to find out detention time. Detention time equal to V divided by Q, V divided by Q. What is V? What is V? Already we have convert the V value 2400 and Q value, what is the Q value? 300. Okay, 300. So meter cube per day. So days to upper side. So we can directly write 8 days. 3 into 24, 8 days. So option B is the answer, 8 days. Do you have any doubts? Any doubt? If you have any doubt, ask. Okay. So in this question, they are already given two values. One value is already given V equal to the volume values 24 lakhs. So we convert into liter to meter cube, and rate of flow already mentioned 300 meter cube per day. So we substitute in our equation, or we can write from these units only. Meter here, meter cube, here meter cube per day. So directly we can divide it, so we will get the day answer. So that is also 8 days. Okay. Very simple question. Okay, next question. As per IS 10313/1982, which of the following factor not influence the sedimentation process in a sedimentation tank? They are mentioning one code here, and in that code they are saying one condition not influence the sedimentation process in a sedimentation tank. They are given some condition. First one, surface overflow values, and second, size, shape and weight of the particle, and C, inlet and outlet arrangement. Option D, pH value of water. Which one? Which one? Actually, surface overflow obviously depends upon our sedimentation process and sedimentation influence value. And also size and shape of particle. The weight of the particle obviously depends upon the sedimentation process. Inlet outlet arrangement also depends upon the sedimentation process. Only one condition we consider, we does not consider one condition, pH value of water. This pH value of water we does not consider for the sedimentation process in a sedimentation. Other three options we will consider for the we will in that three factors will influence for the sedimentation process. Obviously for surface flow rate, obviously for size, shape and weight of the particle, inlet outlet arrangement, that is the regulate the flow of water inside the sedimentation tank. The only we didn't consider pH value of water. Okay, pH value of water. So option D is the answer. So next question. Which of the following test is conducted to determine optimum dosage of coagulant? Which test? Deflector, plate mixers, jar test, Jackson turbidity meter, mechanical flocculator. Which of the following tests conduct to determine optimum dosage? Optimum dosage. Optimum dosage. Famous test actually. Which one? Which one? Any options? 1, 2, 3. Or A, B, C, D. Which one? Option? Option? Option B, jar test. Jar test is used for the calculating optimum dosage of coagulants. If it were too much, 5 jars are fixed in the series order, and we have to find out, we can find out the coagulant dosage value from that test. Okay, so jar test is the test used for find out the optimum dosage of coagulant. Next question. Which coagulant is widely used for sewage treatment? Which coagulant? 1 minute. Lime, alum, ferric chloride, ferric sulfate. Carefully read. The widely used for sewage treatment. Coagulant for sewage treatment. Sewage treatment, not for water, for sewage treatment. Okay. In water, widely used. Which one? In water, which coagulant is widely used? Which? For raw water? Which coagulant widely used? Alum. Okay. Alum used. Then in this case, sewage treatment, which one is widely used? Which one? Ferric chloride. Please note this answer because it's a repeated question. Okay, so please note this answer. So in raw water case, we can widely use alum. In wastewater, so in sewage case, we can use ferric chloride. Okay, option C is the answer. So please note the answer. Next question. In the case the time of flocculation increases beyond this value, the flocks will become heavy and settle down in the flocculation tank itself. Entrapped air will float in the sedimentation tank, break up and defeat the purpose of flocculation, stick to the paddles. So what is the case? In case the time of flocculation is increases beyond this value, flocks. What happened to the flocks? What is flocks? What is coagulation? What is flocculation? What is flocculation? What do you mean by flocculation? Or what do you mean by coagulation? In coagulation, in our water, okay, in our water, too much particle present in this water. So these are mainly negatively charged particle. Negatively charged particle. So in these cases, they are finely separated in different areas in a water tank or water. So in this case, we added coagulant. What is the application of coagulant? The coagulant in positively charged. So this negatively charged particle and positively charged particle attract each other to form large particle. That is the application of, that is process behind the coagulation. So coagulant is used for the colloidal, it help to attract positive or negative charge particle and form some flocks. So in case we introduce fast mixing. Why? So fast mix is increasing the velocity, the movement of particle inside the water. So that will be helping them to form more flocks. Okay. So after in this coagulation, next process flocculation. Okay. So after coagulation, coagulant added, they have formed the big particle, that is flocks. So why? In this case, we introduce slow mixing. Why slow mixing? In some cases, the mixing speed increases. Some cases try to break up, and our process. What is the aim of our process? To combine each other, and it will easy to remove from the water. So in some cases the velocities increases, they are trying to break. Okay. So this is the flocculation. So in our question they are asking the flocculation is increases beyond the 60, the value, beyond the time value, this value. So time for 30 minutes. So after 30, if suppose we consider 30 minutes, okay. After 30 minutes, we introduce again flocculation. So flocculation, we are introducing mixing, and flocculation is process is happen. We choose the 30 minutes for the flocculation, but we are again 1 hour, 2 hour, they take 1 hour, 2 hour, etc. In that case, they are break up and defeat the purpose of flocculation. The purpose of flocculation, they have failed. Okay, so they are trying to break up and separate. They are reached the initial stage. So purpose of flocculation, they have failed. Okay, the fail occur. So this is a option C is the correct answer. So flocculation purpose or coagulation purpose is to form flocks, and that will be easier the removal of particle present in the water. So in the case of time of flocculation increases the beyond the value, in that case break up and defeat the purpose of flocculation. Okay, so option C is the answer. Okay. So next question. Which of the following is a population disinfectant other than chlorine? First one, option A, arsenic. Option B, fluorine and ozone. Which one? Popular disinfectant other than chlorine. After chlorine, which one is popular? Which one? Which one? Ozone. Ozone is a popular. Okay, so chlorine, after chlorine we are using widely in our disinfection purpose, and after chlorine, ozone is the best one. Okay, next, a problem. It's good small problem. The chlorine dose applied is 3 milligram per liter, and residual chlorine after 30 minutes is 0.5 milligram per liter. The chlorine demand 2 milligram per liter, 2.5 milligram per liter, 3.5 milligram per liter, and 0.5 milligram per liter. It's very simple question. We have to find out chlorine demand. What is chlorine demand? What is chlorine demand? What is chlorine dosage? What is residual chlorine? Chlorine dosage. This is a water, same of water. So in this water, the dosage we have to apply disinfection process. So we have to apply chlorine in this water. So the total dosage already given 3. So 3. So chlorine already applied. We didn't know X amount of chlorine applied. X amount of chlorine applied. And the residual, what is residual? Already the after chlorination, the some amount of chlorine present in that water, that is residual chlorine. That is residual chlorine. After 30 minutes, the residual chlorine occurs, that is 0.5. So 0.5 milligram chlorine already present, and total dosage 3. So what is the demand? How much of chlorine? Why how much of chlorine added in this water? So total dosage 3. Dosage equal to chlorine dosage equal to. Please write this equation. Chlorine dosage equal to demand plus residual. Why? So in the water disinfection process, the demand of chlorine plus residual chlorine equal to total dosage. Okay, so total dosage already given in question 3. Demand, I read X plus residual chlorine 0.5. So chlorine demand equal to what is the chlorine demand? 3 minus 0.5 means 2.5 milligram per liter, the answer. Option B is the answer. Okay, it's very simple question. So it's a graph indicating. So graph indicating our values. So this is a formation. the values and the breakpoint happen here. After breakpoint, the residual chlorine occur. Okay, in this case, we are firstly added the total dosage means this. The total dosage equal to demand plus this residual chlorine. Okay. So, two phases are here: formation of chloroamines, destructive of chloroamines, building free resting plus combined chloramines. The chloroamines, they have different type of chloramines, trichloramines, dichloramines, okay, monochloramines, these forms of chlorine. Next question. Also depends upon the chlorination. Which of the following chemical compound can be used for dechlorination of water? What is dechlorination of the water? Please carefully read dechlorination of the water. Carbon dioxide, bleaching powder, sulfur dioxide, chloramines. Which one? Carbon dioxide, bleaching powder, sulfur dioxide and chloramines. Which one is answer? Everyone know chemical compound for use for dechlorination process. We are using bleaching powder and chloramine. B and D we are using the chlorination process. Then two left, A and C. Carbon dioxide, sulfur dioxide. Carbon dioxide we do not consider for the dechlorination process. So last one is sulfur dioxide. What is dechlorination? Dechlorination means we remove the balance, the chlorination, chlorine amount from the water. So that is dechlorination. So in dechlorination process we usually use sulfur dioxide. Other three major dechlorination also are given here: sodium sulfate, sodium bisulfate, activate carbon. So please note this point also. Okay. Please note. So first one, other one sulfur dioxide, 1 and 2 sulfur, sodium sulfate, sodium bisulfate, activate carbon. These four major dechlorination are present here. Okay. So four major dechlorination agents are sulfur dioxide, sodium sulfate, sodium bisulfate, activate carbon. So they can remove the chlorine from the water. That is dechlorination. Please note this part. Okay. So last question. Which chloramine is formed when the pH range less than 4.4? Which one? Monochloramines, dichloramines, both trichloramines and dichloramines, trichloramines. Which chloramines use it when the pH range less than 4.5? If you are range 7, 4.4 to 7. Okay, next, less than 4.4 or greater than. Which one? Trichloramines. In first case, the greater than 7.5, we used it the monochloramines. In 4.5 to 7, we are using dichloramines. Less than 4.4 pH range, we consider trichloramines. So pH range, please note the pH range also. Okay, it's very important also, this repeated question. Okay. It's previous year question. Please note this is a previous question. Okay. So this was our last question. So in this section we discussed it almost 25 question here, 20 plus questions here. So we covered almost population forecasting, characteristics of water and sedimentation process, coagulation, flocculation and disinfection. Okay, these are the main topic today we covered. And just you revise the all topic, all the question and try to solve more question from this area. Okay. So I will come, so we will continue this section, our balance section, that means wastewater and raw water. So this was our last question. So we already we covered almost 20 plus question here. we covered the topic population forecasting, characters of water, sedimentation process, coagulation, flocculations, disinfection. Okay, so you try to revise all the topic from environmental raw water engineering and try to solve more previous year question, more question from this area. Okay, so we will continue our next section, that wastewater engineering and air pollution and municipal solid waste in coming section. Okay, so all the best, study well. Okay, thank you everyone.